So we're going to be talking about both arithmetic and geometric sequences. And the reason we're talking about both of these is because these are two types of sequences that can be written in both a closed form and a recursive form. A closed form essentially means that you can access any of the elements within the sequence just by directly substituting the value. Remember, recursion means you'd have to go through every iteration to be able to get up to that value. Right? Arithmetic sequence is any sequence where consecutive terms are separated by a constant. So for an example, like a really easy one would be something like 1, 3, 5, 7, because all the terms are separated by 2. So the way you can think about that is you just add to the previous term 2, okay? Or you can put it into a closed form to where we have an initial condition 1 plus 2n. Right? So there's a couple ways to be able to think about those, all right? And we'll see in a few moments with an example. Geometric is essentially when you have terms that are separated by a factor, okay? So a really easy example of that might be 1, 2, 4, 8, 16, where what we're doing is we're multiplying by 2 of the previous term to get the successive term. All right, so now there's ways that we can write both of these closed and recursively. All right, so for geometric, these are going to be our general formulas. All right. For arithmetic, these are going to be our formulas. Now D is going to be equal to the difference. Okay, so the common difference between each term. So in this one, D would be equal to 2, because we would just go through and add 2 each time. R is very similar in Calculus 2 when you guys had to go through and you found like that radius of convergence, or essentially what a radius might be. In other words, what factor are you multiplying the successive terms by? In this case, the radius for the example, the very basic example that I had, would be 2, because we're multiplying each term by 2. All right, so let's just take a look at a number of examples where we go through and we try to work with these types of arithmetic as well as geometric sequences. So we're going to find a recursive formula, we're going to find a closed formula, and then we're going to find the 10th term in the sequence. All right, so for letter A, for the recursive formula, remember we have the formula a sub n equals a n minus 1 plus d. Okay? Or in other words, we're going to say that a sub n equals a sub n minus 1 plus 4, because we notice that each of the terms in the sequence is separated by 4. So notice we add 4, we add 4, we add 4 each time to be able to go up to the sequence. Now, of course we need an initial condition. So we're going to say that a sub 0 is going to be equal to 1. All right? So every time you have a recursive relationship or a recurrence relation, you have to give the initial condition. Okay? Otherwise it means nothing. If I want to find a closed form for letter B, well, we could say a sub n is going to be equal to the first term in the sequence, which is 1. All right? So this is our a sub 1 in the sequence, plus d, which we said was 4 times n minus 1. Okay. Or, in other words, we could just say 4n minus 3. Right? And of course we need some sort of initial condition for this. Right? So the initial condition for this would be that n, well, we just basically need to know when n starts. So in this case, n is going to be greater than or equal to 1. All right? And we want to start at 1, because think about this. If you plug 1 into there, that's going to give you 4 minus 3, which is going to give you 1. If you plug 2 in there, that's going to give you 8 minus 3, which is 5, which just happens to be the second term in the sequence. So, and if you really wanted to be specific, you probably should define n to be an integer in here. All right. So this is going to be our closed form of the arithmetic sequence. Both of these do the exact same thing. Okay, so These two are the exact same sequences, but if we wanted to find the 10th term in the sequence, it'd be much faster for us to just go through and use the closed form, because we could just substitute 10 back in. So we could say A10 is going to be equal to 4 times 10 minus 3, which is 37. So hopefully you use this example and you can see the relationship between closed forms, recurrence relations, and then being able to access specific terms in the sequences. As we know in computer science, an array is one of the most useful types of data structures. And this is essentially what we can do to be able to access arrays. We can either do that recursively, which is very expensive in memory, or we could just access the array using an index, right, which is a lot easier. Right. A second example. So we have this sequence. Now, the first thing we notice is that each of the terms is decreasing by 5 each time. So D is going to be negative 5. If I wanted to find a recursive sequence, that would be A sub n minus 1 plus negative 5, or we could just say minus 5. And the initial condition, which we could say A sub naught is going to be equal to 5. So that's going to be our response for letter A. Now for letter B, we need to get to an arithmetic sequence. So arithmetic with respect to a closed form, we could say A sub n. Remember, we're going to put in the first term, which is 5, plus the common difference times n minus 1. When we simplify this, we just get negative 5n plus 10 by simplifying that. Right? Now we need an initial condition. We need to know where to start with this. So we're going to say n is going to be greater than or equal to 1. And you want to check that just by substituting 1 back in for n and making sure that you do indeed get your first term. Right? And we know negative 5 times 1 plus 10 is indeed negative 5, or positive 5, excuse me. And if we want to be really specific, we should say that n is going to be an element of the integers. Last thing we have to do, we have to figure out the 10th term in the sequence. So A10, negative 5 times 10 plus 10 is negative 40. All right, much easier than doing it recursively, although if you wanted to, you could certainly do this recursively. All right. So we're going to stop this section, and then in the next section, we're going to take a look at the geometric sequences.